presence, honorable opponent, ladies and gentlemen, my dear friend, welcome to my doctoral dissertation defense. Yesterday, it's traditional Chinese festival, Mid-Autumn Day. The noon was round yesterday. However, the fact is that the noon will be the roundest in 1 year tonight. In China, we use the same word to express successful and round. So today, I hope I will present successful report for all of you. The topic for my presentation is solutions of difference equations and finite logarithm order and the meromorphic function of finite logarithm order. The dissertation will be divided into 4 parts. The first one is about background information on notations related to Navier theorem. The second one is exponential polynomial solutions of difference equations. The third one is about finite logarithm order solutions of Q difference equations. The last part is meromorphic functions of finite logarithm order in the unit disk. At first, I want to mention some notations. Here is the proximity function. It's average of the measurement of the logarithm of modular meromorphic function f in the circle of regular R. The second one is counting functions. It's related to the points of meromorphic function in the disk of regular R. If we put the counting functions and the proximity functions together, that is Navier characteristic function. Another important definition is the order. The order of a meromorphic function is defined as here. Take the limit shape of these guys as R goes into infinity. The order describes the speed of the growth of the meromorphic function as R goes into infinity. In the first paper, we studied the solutions of difference equations. For some equations, we have already known the solutions of the equations. For example here, if A is not equal to 0, we have already known the exact form of the solutions. However, for different cases, although for the first-order linear difference equation with constant coefficients, we don't know the exact form of the solutions. So what we should do is just study some special solutions of the difference equations. In the first paper, we studied with nonlinear difference equations. And here is a natural number larger than 1. Qz, capital PZ are polynomials. See here is non-zero constant. In the first paper, we studied one of the special solutions, that is exponential polynomial solutions. An exponential polynomial of degree Q can be written as this form. Q is the order of f. H0, H1, and Hn are exponential polynomials of degree less than Q, or polynomials in Z. W1, W2, and Wn are different constants. We call them leading coefficients. If we put the conjugate of the leading coefficients in one set, we denote it by W. If the original point is included, we denote it by W0. The convergence Hall of W is denoted by COW, and the parameter of the convergence Hall of the W is denoted by capital C, COW. Here is the Smith lemma, which was founded in 1977. This lemma was much older than me. Smith used geometric method to calculate the counting functions, proximity functions, and characteristic functions. It says that the characteristic function of exponential polynomial is related to the parameter of the convergence Hall of W0. If H0 is not equal to 0, the proximity function of 1 of f grows less than RQ. if h0 is equal to 0, the quantity function of y of f is related to the parameter of the convergence Hall of W. Here is an example to show how to use Stimis-Lemma. For example, if f can be written as e minus c plus ez, the leading coefficients is minus I and 1. If we put the conjugate of the leading coefficients in the complex plane, here, we have two sets. One is W0, the other is W. The convergence Hall of W0 is this triangle. The parameter of this triangle is 1 plus 1 plus square root of 2. So the parameter of the convergence Hall of W0 is 2 plus square root of 2. So the characteristic function and the counting function can be calculated. Here are two notations. The first one is gamma 1. It's a set of exponential polynomial which has only one exponent term. Alpha here is polynomial and d is a constant. In the set of gamma 1, if d is equal to 0, we denote it by gamma naught. Gamma naught is the subset of gamma 1. In the first paper, we use Stimis-Lemma to study exponential polynomial solutions. Before that, nobody used Stimis-Lemma. This lemma was overlooked for 30 years. We used this lemma for the first time. The result says that for every exponential polynomial, solutions of these nonlinear difference equations belong to gamma 1. Moreover, if the solutions belong to gamma 1, not belong to gamma naught, the order of the solutions is equal to 1. My second paper is about solutions of Q difference equations. For Q difference equation, this lemma plays important role in Q difference equations. However, this lemma only works for zero-order meromorphic function. If we want to know more information about a zero-order meromorphic function, we need another definition, that is logarithm order. The logarithm order of a meromorphic function is defined as here. Keep in mind, there are two log terms here. In the definition of the order, there is only one log term. So we call this definition is logarithm order. Here is another version about the Q difference analog of the lemma on logarithm derivative. Let's compare these two results. In their result, it works for zero-order meromorphic function. In my result, it works for finite logarithm order. It's a subset of zero-order meromorphic function. In their result, the right-hand side is just small term. In my result, the right-hand side is related to the logarithm order. In their result, the equality holds outside an exceptional set. In my result, there is no exceptional set. But later, I taught study this kind of Q difference equations with rational coefficients. The modular of Q here is between 0 and 1. They have two important results. The first one is the logarithm order of the meromorphic solutions of the equation 1 is at most 2. The second result is the logarithm order of any transcendental meromorphic function of the equation 1 is exactly 2. In the second paper, I still studied this kind of Q difference equations. The coefficients here are any finite logarithm order meromorphic function, not only logarithm order 2. The coefficients here is not only between 0 and 1. The case of the modular of Q larger than 1 is also included. If the coefficients satisfy this equality, we have the conclusion that the logarithm order of the solutions is equal to the biggest logarithm order of the coefficients plus 1. Here is an example to show the application of the theory. If we denoted W1 is equal to 1 minus C, the logarithm order of the W1 is equal to 1. W2 is the product related to W1. Modulo of Q here is larger than 1. It's easy to check that W2 satisfies this Q difference equation. According to the theory, the logarithm order of the solutions is equal to the logarithm order of the coefficients plus 1. So we have the logarithm order of the logarithm order of W2 is equal to 2. Similar, W3 is the product related to W2, and W3 satisfies these Q difference equations, and the logarithm order of W3 is equal to 3. Step by step. At last, Wn satisfies Q difference equations, and the logarithm order of the Wn is equal to m. The third paper is related to the meromorphic function of finite logarithm order in the interdisk. It's well known that there is a big gap between the bounded function and the admissible function in the interdisk. The concept of the logarithm order can be bridged this gap. That's the reason we study some property of the meromorphic function of finite logarithm order in the interdisk. The whole idea of this paper comes from my supervisor, Yang. Here is the definition of the logarithm order of a meromorphic function. It's similar as the case of complex plane. According to the definition, if f is meromorphic in the interdisk, after calculation, we have the first integration convergence. The second integration doesn't convergence. Just as in the line of the finite order case, we define this definition. If Zn is infinite sequence of points of zeros of the meromorphic function, its logarithm exponential convergence of zeros of f is defined as here. Take the biggest low bounded of the constant such that this sequence converges. We have the conclusion that the logarithm exponential convergence of zeros of the meromorphic function f is less than or equal to the logarithm order of f. It's well known that the plastic product is analytic in the interdisk under the assumption of plastic condition. If we relax the plastic condition into this equality, let's consider Zhi product Tz. Zhi product is analytic in the interdisk under this kind of assumption. Zn here is infinite sequence in the interdisk, and Zn is the zero of the Zhi product. We have the result here. The logarithm order of the Zhi product is equal to the logarithm exponential convergence of the zeros of the Zhi product. Just by this result, we note that for every meromorphic function of finite logarithm order can be written as the quotient of the two analytic functions. We denote it by f1 and f2. The logarithm order of f1 and f2 are less than or equal to the logarithm order of f. Here is the definition of the logarithm m order. Logarithm m order defined as logarithm order of logarithm mRf. For analytic function in the interdisk, if we write it as a Taylor series expansion, we use μRf to denote its maximum term. We have the result about the general relationship between the logarithm m order and logarithm mu order. Moreover, if 1 minus r times mu rf is bounded away from 0, the logarithm m order and the logarithm mu order are the same. From this result, the general relationship between the logarithm m order and the logarithm mu order. We want to know under what kind of assumption the logarithm m order and the logarithm mu order are the same. We find one of the assumptions, that is Hadamard gap theory. Here is the definition of the Hadamard gap theory. If we write f as this form, the power of z satisfies this equality. We call f is Hadamard gap theory. The conclusion is that if f is a Hadamard gap theory, its logarithm m order and the logarithm mu order are the same. Here is the result about Weyman-Balinon theory of the finite logarithm order case. If we divided this theory into two parts, the first one is central index is unbounded. The second one is central index is bounded. For the unbounded case, there is one more assumption. For the bounded case, there is no this kind of assumption. Both of the case, we choose some point such that the modular of the function f is closer to the maximum modular. We have the similar conclusion. Both of the right-hand side are the same. Both of the left-hand side are the same. The right-hand side are different. For the bounded case, the power of the logarithm term is q plus epsilon. For unbounded case, the power of the logarithm term is q times maximum 1 and rho plus epsilon. The last part is about the inverse problem of value distribution in the unit disk. Here is the definition of the deficiency value. According to the second fundamental nonlinear theory in the unit disk, we know that for the meromorphic function, the sum of the deficiency value is at most 2. For analytic case, the sum of the deficiency value is at most 1. The inverse problem of the value distribution in the unit disk is that can we find an analytic function in the unit disk with the given deficiency value? The conclusion is that under this kind of assumption, the inverse problem can be solved for any finite logarithm order. Okay, that's all. I ask you, my honorable professor, as my opponent, to present the record, which you consider my thesis will require.
Okay. First of all, before going to questions and comments on your thesis, I shall make some statement on the topic, on the questions you have dealt with. Okay, the topic of the thesis is the so-called value distribution of meromorphic functions. It comes from a very long time, this topic, but it shows nowadays many signs of vitality and activity. Okay. The first results in this area were due to French mathematicians, Borel, Picard, but later on, in the first decades of the last century, a Finnish mathematician, Rolf Nevanlinna, who was born here in the town of Joensuu, introduced new methods and modified the ideas present at those times, and he created what it is known as the modern value distribution theory or Nevanlina theory. Okay, Nevanlina theory was flourishing all over the last century, and it was a main chapter in function theory, but in the last times also extended to different other areas related to different areas like differential geometry, like for instance was extended to higher dimensions. There were found some connections with number theory, and they were found in different areas some analogs to Nevanlina theory. Some particular analogs are considered by the candidate, Zhi-Tao. For instance, those analogs, difference analogs of Nevanlina theorems and Q difference of Nevanlina theorem. Okay, but he also, he applies these analogs to the study of difference functional equations on Q difference in a similar way as classical Nevanlina theory was applied to the study of different qualitative behavior of solutions of differential equations. Okay, this is part of the thesis. There is other part which deals with classical problems, with problems, particularly specific problems in classical Nevanlina theory. He pays attention